So in part two, we will talk about what is the Laplace transform. Basically, Laplace transform, it is try to transfer the ordinary differential equation, become the algebra equation. So because the ordinary equation, it is difficult when we try to solve the ordinary differential equation. Sometimes it is very more difficult, and we try to transfer the time domain. Usually uh, our function will be related to the time, so it will be, for example, it will be certain function, and along the time you will have, for example, you will have position, velocity, and acceleration. And the position, velocity, acceleration, it will follow certain Garmon equation. It will be the ordinary equation. So we see this response in time, along the time. So we call it is a time domain. But when we transfer, if we see this function not in the time, we transfer to the other aspect. We transfer to the frequency domain. For example, a sine function. A sine function in the time domain, it will look like this one. But in a frequency, if the duration, this one is the 2 pi, is 1 second. Let me say it will be 1 second. Okay. So in the frequency domain, here, if the unit is frequency, is hertz, this kind, and the magnitude here is 1. This kind of function, it will become a point. We have, this is the magnitude. We will say the magnitude. The magnitude is 1. We can say this function in the frequency domain, it is 1. Magnitude is 1. And the frequency is also 1 hertz. So it will become a point. Okay? So we transfer they are the same thing. They represent the same thing, but we see this kind of signal in different domain. So basically, the Laplace transform try to transfer the function in different domain. We transfer the function from time domain to frequency domain, and therefore the calculation, it will become algebra equation. It will be easier to solve the problems. So we use a lot of the Laplace transform to help us to solve the system dynamic equations. So we will define ft is a time domain function, and as t smaller than 0, it means the past time. The t is 0, and we will say ft will be 0. So it means the function before 0 must become 0, but after the 0, it can be any kind of function, but it will be a function of t. So we call this kind of function ft. And s, it is a complex variable. S can be any complex number. It can be, like, for example, this kind of phone. It should be a complex number. It can only have real part, or only have imaginary part, or like it can have both of value here. So S, for example, it can be 1 plus 2j or 2 plus 3j. We don't know because it is a variable, but it is a complex number variable. And we use the arrow, this symbol. it means it is operational operation, the Laplace transform operation. And what is Laplace transform do? It will be this symbol actually we will do a Laplace integral. So Laplace integral will be exponential negative st, and the integral from 0 to infinity. Because our function smaller than 0 is 0, so we only need to integral from 0 to infinity. And Laplace transform will be, it will transfer the f of t become, after the Laplace integral, it will become f of s. So f of s will be the Laplace transform of f of t. So basically, you can see the symbol will be, we will use a L, function of t, and then this symbol, it means we do the Laplace transform become fs. And what will be the operation? Actually, will be f of t multiply exponential negative st, then integral from 0 to infinity. And this operation, basically, it is to find a correlation between the f of t and the exponential negative st function. So for example, if f of t is like for example, as a sine function, it was 1. And when we do the operation, if this function is also like this one, they are the same function, okay? So when you multiply them together, you will get certain value. The value will be very large when you integral. So when you multiply this and this function, each point, multiply each point, it will become a positive value. And when you integral, it means the summation, all of the summation. When you multiply this, it should be look like this one. And when you do the integral, it will become certain value. So if the function, these two functions very similar, the value will be larger. So actually try, but we can assign different s here. If the s is different from the function, if the function may be look like this one, it may be a more high frequency signal. So when you multiply these two functions and do the integrations, you can see the 0. This whole function will become 0. It means this signal is not really correlated to these two signals. They are not correlated to each other. So basically, this operation is try to find a correlation between this function of t and this signal. But this signal, it can be any kind of signal. It depends on what is your s. How do you assign the s? So remember this equation. When we want to find a Laplace transform of function of t, we need to do the Laplace. We need to do the Laplace transform, Laplace integral. So it will just follow this function. So when we do the Laplace transform, the symbol will be Laplace transform. Function of t become fs, and we do something like f function of t multiply exponential negative st integral from 0 to infinity. And when we do the inverse Laplace transform, the symbol will be, we use the negative one here. It means it is the inverse Laplace transform. So we want to transfer the Laplace transform f of s become the function of t, f of t, we will write some symbol like this one. Here is the definition, the symbol definition for the Laplace transform. And I will talk about the property of Laplace transform. So the following table will be the conclusion. Those table, it will help us to do the direct calculate transform direct do the Laplace transform operation. So basically, you will need to use the following. It may be 4 or 5 following 4 or 5 slide. It will be very important. The most important in chapter 2 is this loss table, because after you understand how do we get the conclusion in loss table, you will not do any mathematical calculation. You would apply the function, the conclusion here. So we will talk about the property one by one, and after we talk about the table, in the following we will have several proof of the Laplace transform. So it will be more easier to let you to remember what is the table's conclusions. So for the property, first one will be the superposition. If I have f1t and f2t that have certain value a, b, so after we do the Laplace transform, it will be equal to, we can do the Laplace transform for f1, and we can separately do two Laplace transform, f1 f of s and f2 f of s, and then direct multiply the gain and add them together. So we call it is the superposition. You don't need to have the whole do the Laplace transform for the whole function. We can separately to do the Laplace transform for the different function, and after we get the Laplace transform for different function, then we can do any algebra, the same algebra operation here to get the Laplace transform for the whole for this whole function. And so this is, we call it is a superposition. And then differentiation and integration, it is a very important property here. So if I have a function, it is a df, it is do the differentiation for function of t one time. In the Laplace transform, it will be, you can see it will be s multiply the f of s. If you, because find this function might be easier, find the, if we already do the Laplace transform, we already know this function. And how do we know what is the f? What is the, just here, what is this function? Do the Laplace transform. Basically, you can directly use the result here. S multiply function f of s minus the initial value f0. So this is the time domain function. This is the Laplace domain function, Laplace transform function. So so this property tells us s actually it is the operation symbol of differentiation. So apply the same rule. We can find, if I do the double differentiate, the solution will be, you can see the double differentiate function of s minus s of 0 and the minus f0 dot. So this will be the original function of time, and this will be the differentiate function of time. as time equal to 0, the initial value. So you will just remember you will use this kind of function to help you to do the Laplace transform in the following material. So when you apply the same rule as we do the differentiation n time, you will follow this whole equation. Okay? And so in this function, actually just tell us the most important thing is S. It means it is the differentiation operation. When we do the differentiate in time domain, it means we directly multiply S in the X domain for the f of a function. So when we do these things, multiply S, it means we do a differentiation operation in time domain. And so for the integration, it is similar to the differential. If I say multiply S is a differentiation operation, so the inverse of S, 1 over S, multiply 1 over S, we call it is an integration operation. So if I do the integration for the function of t, it means in the Laplace transform, it means we will multiply 1 over S, multiply function of S. And you also need to, here will be the initial value after the function after the integration, function of the integration, but the time equal to 0. What is the initial value? So you will assign the initial value here over S. And then, so the conclusion here, when you multiply 1 over S in the Laplace transform, it means you do the integration in a time domain for the function of t. Then frequency shift. If we have a shift, this is a shift function. Function of S. If function of S is look like this one, after we have a function of S plus A, the function will become, it means we have a shift. It will become something like this one. The shift here will be A. Okay, so after we have a shift in the Laplace transform in the S domain, we call S domain, and the S domain is related to the frequency domain. So we say if we have a frequency shift in the time domain, actually it is dual operation. It will be multiply exponential negative at. You need to remember this property. And then the time delay function. When you observe time delay here, ft minus a, it is similar to the shift. The property 11 is the shift in the frequency domain, but here we have shift in the time domain. So if we have shift in the time domain, we call it is a, if we write this form, it is a time delay. So f of t maybe look like this one, and after we shift, maybe the f of t maybe look like this one. After we have a shift, it may look like this one, and we have the shift will be the alpha, the delay will be the alpha. Here is alpha, and we need to let the, because remember our function should be, original function should be look like this one. should be 0 as time smaller than 0. And so after the shift, we need to let this part become 0. So you can see we will multiply a function here. The function is 1 t minus alpha. What is 1t function? 1t is a step function. This function actually it is a step function, and after the time delay for this function, it will become t minus alpha. So it will become this function. So when you multiply this function with the function of t may become this multiply this. It will become this kind of function. Okay. So this function is the actual function we want. So the same rule, similar to the frequency shift, the time shift, here we call time delay. If we have a time delay in the time domain function, it means we multiply exponential negative as alpha in the Laplace transform. So you can try to remember the property 11 and 12 in the same time because they are the similar rule. They have the similar rule. If I have frequency shift in the property 11, if I have a frequency shift, it means I need to multiply the exponential st in the time domain. And in property 12, if I have a time shift, time delay, I have to multiply the exponential minus as alpha in the frequency domain. They are the same rule. Okay. And if I multiply time, so it becomes t multiply f of t. In the Laplace transform, it will be do the differentiate in the Laplace transform, and the differentiate the variable is s. So and add the negative. So if we multiply tn power, it will follow this equation. And the t2, you just need to remember this one and this one because you will use a lot about multiply t or t2. And if you sometimes you need to multiply t, and you can just follow this rule, this equation. So the conclusion tells us it will be if you multiply t power 2, it will be do the differentiate twice. If it is n time, you will do the differentiate n time, but each differentiate you need to multiply -1. Here it becomes positive because we multiply -1 power 2, it will be 1. Okay. So after this, in the property 17, we call the time scaling. So in the time scaling, if time scaling, it means if my original function is f of t is this one, and this might be 1 second. After the function become t over a. So what will be the function look like? So the function will become this become a. Okay, so it will be a scaling. You can see if it is scaling along the time, so we call it is a time scaling. If we do the time scaling in the time domain, it mean in the frequency domain, it will be you need to multiply the scale factor, and also the function will become function of as. Okay, so here is the conclusion. In the following slide, we will have the proof about how do we get that. But the proof basically it is just help you to remember the conclusion. The most important property just here, and you will need to use this table because our quiz or our exam, I will let you open the book. So basically, you don't really need to remember loss conclusion, but you need to know how to use those conclusions. So you still need to do several practice. And the property 27, we call it is the initial value theory. So if we want to find the value, the initial value of function of, if I have a function, I want to know what is the value here. It is the f0 plus. It means in the very beginning, the value very approximate as time approximate to 0. What is the initial value? We use this symbol because f smaller than 0 should become 0. So if the time is very approximate to 0 but a little large than the 0, what is the initial value? So you can use the limit function to let t equal to approximate to 0 to find a value, or you can find a value in the Laplace transform, in the Laplace transform function. So in the Laplace transform function, if you want to find the initial value for a function of time, it will be you need to multiply s in the Laplace transform and assign s equal to infinity to find the value. So you can, if you apply this equation, you can directly find the initial value of function of t. And the final value, if I want to find, if a function maybe look like this one, I want to find what is the f infinity, what is the final value here, what does the value come, it may be certain value or become infinity or become negative infinity. So how do we find this value if we already have the Laplace transform? So if you want to find the final value, it will be you need to multiply s. You can see multiply s and assign s equal to 0 to find what is the final value. Okay. And here you did not use a lot, but this is a very actually the last properties actually is a very important property, but we do not really use a lot in our course. But in a signal processing or in Fourier transform, we will use a lot of this kind of property. So it tells us in the convolution in the time domain, actually it is the multiplication in the frequency domain. So the same rule, when we do the convolution in the frequency domain, it will be in the time domain, it will be the multiplication in the time domain. Okay, so you just remember if I do the convolution, this is a convolution function in time domain. In frequency domain, it will be direct multiply these two Laplace transform. Okay. The Laplace transform pair, it already give you the what is the Laplace transform for specific function. So for example here, this is we call the unit impulse function. it is this kind of function. It is only a pulse in a very short time, very short time, and the unit is 1. So we call it unit impulse. This is the representation symbol for the unit impulse function. So unit impulse function, the Laplace transform will be 1. And here I just go through all of the function and what is the Laplace transform, and you can try to memorize several simple functions. Like unit function, the unit impulse, the Laplace transform is 1, and the Heaviside unit step function, this is 1t. 1t, we call it is a Heaviside unit step function. So this kind of functions look like this one. Unit is 1. So this is 1t. It is the unit step function. The Laplace transform is 1 over s. Okay, and so the t, if our function we call unit ramp. If our function is this one, this is ramp function, and if smaller than 0, the function is 1 over s power 2. And you can then the last one, the fourth one will be the t power 2 over 2. So it is a parabolic function. It is look like this one. This function, it will be 1 over s power 3. So when you observe this 4 function, this 4 function, you can see they have the differentiation and the integral relationship. So when you do the differentiate for this one, you did parabolic function, it will become this one. It will become t when you do a differentiation. So you can understand if this one is f of s, when you do the, and this one is ft. So when you do the differentiate the ft dt, you can get t. This is 2t2. So this one we can get the t. So we can understand, we can directly apply the property of Laplace transform property. The differentiation is basically it is multiply s. So s multiply fs, and the fs is 1 over s3. So s3 multiply s, it will become 1 over s2. So we can get the Laplace transform for the unit ramp according to the unit parabolic function. And remember, in the property we still have certain initial value here, but if we assume initial value is 0, we can directly ignore the part. So you can observe this 4 1 here, go here, multiply s, so it's differentiate, multiply s. So Heaviside unit step function, it is the differentiation of ramp function t, and this go up step function do the differentiation. This function do the differentiate, you will get the impulse function. Okay, so if you go from the impulse function, when you do the integration, you can get the step function. So you will multiply 1 over s. And from the heavy side unit step, go to the ramp. When you do the integration, you can get the unit ramp. And from unit ramp, do the integration, you can get unit parabolic function. So you need to understand those basic functions. They have certain differentiate or integration relationship. And we will use these 4 functions in our whole semester. So if it is more higher order, it will follow this dual. Okay. And exponential negative AT. This function is very important because our response, dynamic response, is follow a lot of dynamic response will follow this kind of function. Exponential negative AT, it will be this kind of function. It will decay because our dynamic, we have the temperature, the energy will be loose and until go to certain balance point. So our response will always converge in certain point or converge in 0. So it will follow this kind of function, exponential negative AT. And this, when we do a Laplace transform for this function, it will be the 1 over s plus a. If it is t exponential negative AT, it will be 1 over s plus a2 power 2. Okay. And if it is a more older, when you multiply, we have, do you remember we have the property in the previous slide? When you multiply t power n, we can also directly get the Laplace transform through this one. If this is fs, and so we can get the Laplace transform according to previous. If we multiply t or multiply higher order, you can go to see what is the equation. See how do you get this result according to this one to here. Okay, see if you know how to apply the property of the Laplace transform to help you to get the solution. And so these 2 functions, this 1 to 7 are very important function. We will use a lot. So it is better to remember those relationship, the pair. And in this table, those red block, those 9, 10, 11, 14, 15, 16, 17 will be also very important Laplace transform function you may use a lot in this semester. And in this table, it is better to memorize the 2 functions, sine omega and cosine omega t. Okay, omega is the frequency, it is a radius. So omega will define the oscillation frequency. For example, if omega is 2 pi, it means when you it rotates 330 degrees in 1 second. Okay, so this point is 1. So if it is this one is a sine 2 pi t. If it is the sine pi t, maybe I draw here, you can compare. The oscillation will be quickly. So because 0.1 because it will become slowly, the oscillation will become slowly because as time equal to 2, it will become 2t, 2 pi. So 2 seconds, it will only have one cycle of sine function. Okay, so the omega will define the smaller. If you have a smaller omega, it means the oscillation is slowly. We have a low frequency signal. So sine omega t, Laplace transform for sine omega t will be the, you can remember it cosine and sine in the same time. In the denominator, you will have s2 plus omega 2. For sine, you just put omega here. For cosine, you put s here. Okay, so you can try to remember these two functions in the same time. Sine omega t will be omega over s2 plus omega 2. Cosine omega will be s over s2 plus omega 2. And we will also, so these two functions you should try to remember it. And then the 14 to 17, you don't need to remember. When you will use it, you can just try to find this table and directly use the result. We will have a lot of functions like 14 and 15 and also the 16. So if we have 14 functions like this one, the Laplace transform will be 1 over s multiplied s plus a, 1 over a. Remember the function, it will be 1 minus exponential minus at. Okay, so this kind of function, it will look like when you apply the t equal to 0, it is 1. So initial value is 0, and then it go to the only this part, it will be 0 go to 1. But we multiply again 1 over a, so the maximum value will become 1 over a. You will try to go to the 1 over a and then converge in the 1 over a in as time equal to infinity. So this kind of response, it is the step response. Okay. And if we have the form look like this one, two exponential function, but we have different decay ratio, a and b. So this kind of function and a certain gain, this kind of function can convert to 1 over s plus a multiply s plus b. So just try to remember this 3 is most important, and the other you just need to know. If you see some form look like the lost form, you can directly try to find a solution through the pair, through this table. And in this table, the other two important equations will be this 20 and the 21. 20 and the 21, you can directly get a solution through the property, the frequency shift property. Please try to see what is the frequency shift property in the previous in the properties table. So we already know this equation. If this is f of t, and this is the Laplace transform is f of s, it is 1. It is the omega s2 plus omega 2, and then we multiply exponential minus at here. It will become exponential minus at f of t. Okay, so if we multiply exponential at, what is the Laplace transform? You can check the frequency shift property in the property slide to see if you can directly get a result like this one. So multiply exponential at in the Laplace transform. Actually, it is the frequency shift. You will get this one. Okay, you need to remember here is exponential negative at. If you multiply exponential at here, will become s minus a. So the cosine exponential the 21, we can also use the frequency shift property to get the solution. It will become this one. We have the frequency shift in the related to the s variable. Okay, so most important in this slide is these two functions. And the other our second order differential equation solution will be 22, 23, and 24. So you will also use a lot of the Laplace transform for this loss kind of function, because we basically the solution for the second order it will be 22 and the 23 and 24. So you don't need to remember it, but it is you need to have basic knowledge about loss. This, if you see this form, you can understand what is the original solution. It is related to they will be related to the second order differential equation solution. And 25 to 31, if you can see certain function, it is look like 25 to 31. You can also directly apply the Laplace transform. You can directly get an answer, and you just have a look to see what would be, because loss function is we did not use a lot in this semester, but you can, if you really see loss kind of function, you can directly apply here by the pair. So in the previous property table and the Laplace transform pair table, we already the most in chapter 2 most important table is just the loss table I talked about it. You need to know how to use loss table to help you solve the Laplace transform. And then following, I will talk about how do we get the Laplace transform of f of t for different function. It is a proof for those table conclusions. So here you don't, if it is several calculation, and we will not really do this kind of calculation in our semester, because we will directly apply the result. But loss here, if you know how do we get the function, maybe it is easier for you to remember the Laplace transform property and also the Laplace transform pair. So if our function is an exponential function, and we have certain gain a, what will be the Laplace transform? So f function of f of t is a multiplied exponential negative alpha t. So when we use the Laplace transform arrow here, it means we need to multiply, we need to find a correlation, multiply a exponential minus alpha t multiply exponential minus at, and integral from 0 to infinity. So we need to, you see, I multiply the Laplace transform integral. Laplace transform, this is the Laplace transform integral, okay, with the original function. After I multiply this and do the integrations, so this one, this exponential minus alpha t multiply exponential minus st, we can directly combine together and then move, because a is constant, it did not relate to the time, so we can move the constant outside a here, and this becomes exponential minus alpha plus st. And when we do the integral for this function, you will get 1 over s plus alpha. Here will be, you need to I give you a reminder. If I have a function, it is exponential ct dt. When we do the integral for this function, exponential ct, you need to remove the constant term, divide the constant term from the except the t. The constant term is c, so it will be 1 over c, and put the original function here. Okay. So for this function, when we do the integral, so this part, it will be you will put the original function here, and you need to remove the constant term except t. So the constant term will be minus alpha plus s. Okay, and we need to integral from this 0 to infinity, so it will be 0 to infinity. When we assign infinity here in t, you get the first term. When we assign 0 in t, you get a second term. So if exponential negative infinity is become 0, so this one becomes 0. So this whole term will become 0, and this one will become, when you put 0, exponential 0 is 1. This term is 1. So we get the a over alpha plus s. So we get this solution. Okay. So remember, try to remember this conclusion. The conclusion is a multiplied exponential negative alpha t. You can get the Laplace transform. After Laplace transform, the solution will be a over s plus alpha. Then we will talk about the step function. If we have a function, it is f of t equal to a as t larger than 0. So this function will look like this one. And the amplitude is a. What is the Laplace transform? So we also multiply the Laplace integral, Laplace, and this part is the Laplace integral. Okay, so the solution will be the a over s. Remember, if we have functions, this one is actually equal to this one, a multiply 1t, and 1t, this Laplace transform is 1 over s. So the solution here will be a over s after the Laplace transform. So when we directly do the calculation for the integration, we can see here we can move a outside and do integration for this function. Remember the rule, keep original exponential function, exponential minus st, and then move the constant term. It will be, move the variable but constant term except the time. So we can move the other all of the term before the time. Minus s divide in the outside 1 over minus s and multiply the constant term a. So we get this one, and when you put infinity, this term becomes 0, and this term become 1. So we can get our solution will be a over s. Okay, so this is the step function, and so you can understand if our function is unit step function, 1t, the solution will be 1 over s. We do the similar calculation. You can check if you understand how do we do the integrations. And here we will talk about the ramp function. If our function is the at, so this function is a function we call ramp function. It will be look like this one, and the a define the slope. Okay, it is the slope of the ramp function. So when we do the Laplace transform for the ramp function, so we do the Laplace transform for the ramp function. We also multiply the Laplace transform integral. Okay, and when we solve these problems, we will need to apply the integration by part. Let us remind what is the integration by part. If I have a variable u and the v, so u and do the integration from a to b and the b along the parameter b. The solution will be u multiply v and the a to b minus integral v and the differentiate along the parameter u. So according to this rule, we can treat like u is t equal to u and the dv equal to exponential minus at dt. We treat like this whole term is dv. Okay, so after we treat u is t and the dv is this term, we can get our solution will be, so this part will be u equal to t and the v equal to integral of this term. And the integral of this term, it will be, you can see u is t, now then the du equal to dt, dv equal to this one. So after we use the integration from along the t time from, so you can get u will be equal to this term. Okay, this integration will be we keep the original part and remove the part except the time, minus s to the denominator, 1 over s, negative s. Okay, so we get this one. So u will be this term, v will be this term. So we put this here, and the integral from 0 to infinity, minus integral from 0 to infinity, and then we put u will be v will be again here, and the du is dt. Okay, so then we can do we can get the final solution here. For this part, as we assign the t equal to infinity, this part becomes infinity, exponential negative as infinity, it will become 0. As we assign t equal to 0, is the t will become 0, so it will also become 0. So this whole term for this part is actually it is 0. We only have this term. And when we do the integration again for this term, you can see we can remove the s outside, because s is not a parameter related to the time, the differentiated variable time. So we can move s outside, a over s equal to this one. And you should already know how to do the integration for this one. We will keep, it is similar to, it will be here. Okay, so we will keep the exponential minus st and put the part before the time, negative s in the denominator. And when we assign 0 to infinity, this will equal to exponential minus s infinity over minus s minus exponential minus t 0 minus s, and this is 0, so we only have this term. This is 1, so our for this term actually will be the 1 over s. Okay, so 1 over s multiply a over s, we get the solution will be a over s power 2. So after this proof, you should remember, you should try to now know if I have a function, it is a ramp function, is f function of t. You need to remember this Laplace transform for the ramp function. After Laplace transform, it will be 1 over s power 2. Okay, remember this one. So when I multiply certain gain, it just multiply the gain in, here. Okay. Then we will talk about a sinusoidal function. So if we have a function, it look like function of t, f of t equal to a multiplied sine omega t. So it will be this kind of function. Amplitude here is a, then here will be negative a. If I have this function, what is the Laplace transform? So when we do the Laplace transform for this kind of function, we also multiply the Laplace transform integral here. Okay, and we already know the exponential j omega t in the complex number. In the part 1, we already know exponential j omega t actually will equal to the cosine omega t plus j sine omega t, and the exponential negative j omega t will be equal to cosine omega t minus j sine omega t. So we can know the sine omega t actually will be the 1 over 2j exponential j omega t minus exponential negative j omega t. Why do we transfer to this form? Because if we transfer to this form, you can see exponential j omega t. This function is, we already know this function's Laplace transform. Okay, this function's Laplace transform is s minus j omega, and this function Laplace transform is 1 over x plus j omega. In the apply the exponential function pair, remember exponential minus alpha t, the Laplace transform is the s plus alpha 1, or 1 over s plus alpha. So if alpha become the j omega, we don't have the negative here, so in your solution will be 1 over s minus j omega, and this one is just similar to this one. Alpha become j omega, so we can get the solution will be the 1 over s plus j omega. So when we transform the sign become the exponential form, it will be easier for us to solve our equations, because we already have the exponential function, the result of this exponential function. So here, when we replace to this term, and 1 over 2j, a over 2j put in the outside because it's the constant term, and we can do this part is we call it superpositions. We can do the 2 times Laplace transform. We can do, it will be equal to direct to Laplace transform for the whole function. So this part actually we do 2 times Laplace transform, exponential j omega t exponential minus st dt and the minus, we do 2 times Laplace transform according to the superposition property. J omega t exponential st dt. Okay, so we can directly apply the rule, the pair for the exponential function. So we will get this solution. And when you try to merge these two functions, you will get this one. Okay. So this part is just simple complex number calculation. You need to let the denominator become real part. The real part is s2 plus omega 2. This part is also the same thing. So after you let the denominator become the real part, you add them together, you will get the solution will be the a omega over s2 plus omega 2. So if you in this slide, you need to remember the function sine omega t. When you do the Laplace transform, it will be omega over s plus s2 plus omega power 2. And we have a game here, so the solution for this slide will be a omega over s2 plus omega 2. For the translative function, our original function will look like this one. It will be ft multiplied 1t. And we use this function because ft might not be 0 as time smaller than 0. The ft might be some function like this one. But after we multiply 1t is a Heaviside step function. When you multiply these two functions, it will become this one. Okay, so we write some function like ft multiply 1t, and when we have a time shift alpha, this is time shift alpha, our function will become ft minus alpha 1t minus alpha. Okay, and remember the conclusion in the Laplace transform property. If we have a time shift, it means in the Laplace transform, the solution will be multiply exponential negative alpha s, and alpha will be the time shift value. So the conclusion is this one. Okay, remember this conclusion, and here we will prove how do we get the conclusion. So when we do a Laplace transform for this function, we also multiply the Laplace transform integral, and we can do the variable replacement. We assign the tau equal to t minus alpha, so we can replace this function become the f tau 1 tau, and so we know t is equal to tau plus alpha, so we can replace t become tau plus alpha, so we get this one, and our integration time will be, because of this function, it will become the alpha to infinity. Okay, and actually it will become negative alpha to infinity, because this will be the, if we put, this is 0 to infinity, and if we put 0 here, it will become the negative alpha, so we will integral from the negative alpha to infinity. Okay, and the negative alpha, actually it is 0. Negative alpha to 0, it is 0, so we can replace negative alpha become 0. So you can see this form. Okay, so and then 1t is 1, so we let it become 1. Just remove this 1. It will become f tau exponential minus s multiplied tau plus alpha, and we can separate this term become exponential minus s tau multiplied exponential minus alpha s, and exponential minus alpha s is not related to tau. So when we do we can move outside the integral part. So when we remove this outside, you can see this form. This form is basically the Laplace transform for the function of t. Here will become function of tau. So this part actually will be the fs. Basically, we already have if we know the function of t is we already know the function of t and know the Laplace transform for function of t. We have a translation function, the time shift here. It means that in our Laplace transform, we can directly get a Laplace transform through the fs, the original Laplace transform function f of s. It will be directly multiply the exponential minus alpha s. Okay, so this is the proof. So after this slide, you need to understand if you have a function, it has certain time delay, time shift. The Laplace transform. Basically, you already know the Laplace transform for f of t. F of t Laplace transform is f of s. And if I have certain time delay, time shift, the solution should be exponential minus alpha s multiplied the original Laplace transform function of s. Okay, you need to remember this property. This is a very important property. And if we have the function is a pulse function, if it is a pulse function, the pulse function is some kind of function look like this one. The t0 is a certain value, certain duration. It can be large or small. If t0 is very small, it will become the impulse function. But here, if it is not small, it will be going up and going down in certain duration. We call it is a pulse function. And the area for the pulse function will be a. Okay, so if you use a over t0, we can generate a pulse function by two unit step function. For example, for this one, when we see this function, we see this one. What is this one? This one is the a over t0. Is this one? And what is this one? What is if I use this one, only this one, not the negative part, it is a shift, time shift, but the shift is t0. A over the amplitude is a over t0. So when you use this function, the upper function minus the below function, you can generate a pulse function. So we can write the pulse function will be the composition of two-step function. So it will be this one. After you understand this one, so when we do the Laplace transform, basically we try to do the Laplace transform, apply the superposition theory in two-step function. So we already know what is the step function Laplace transform. It will be 1 over s, so it will be a over t0s, and this is the step function and the delay. When we apply the delay, time shift, time delay, we will multiply exponential minus alpha t here, alpha s here, and the delay here will be t0. So the alpha actually we can apply alpha become t0. So we can get this term Laplace transform for this delay step function. Actually, it will be the multiply the delay. What is delay? Delay is t0 minus t0, okay, s. And what is the original Laplace transform function? It will be the step function. It is 1 over s. So we get this term. We get this part. Okay, and then when we multiply again, a over t0, so we get the whole solution will be this one. So you can see when we do the Laplace transform, we will try to use the property or the pairs from the table to help us solve the to calculate the Laplace, to get the Laplace transform. This is a good example to let you understand why do we need the table to help us to get a Laplace transform result. So the solution will be this one. Okay.